Now that we know about the nature of covalent bonds, and we know about electronegativity differences and can predict polar covalent bonds, we're in a good position to learn the rules for drawing Lewis structures in general. Keep in mind that these Lewis structures, which represent electrons as either dots or dashes, is just a very simple model of chemical bonding, but it has great predictive power, which is why we use it. It's much simpler than doing the complicated computer quantum chemistry calculations that would be necessary to predict accurately bond lengths and bond angles and bond orders. This is a model that we can write down and just with a few tools like a periodic table make a number of useful predictions about number of bonds, and as we'll see next chapter, it's a basis for predicting shapes of molecules, and shapes play a very important role in the properties of substances. So I'm going to go over the rules for drawing Lewis structures. I'm going to go through the rules with just one little break, and then in a later talk I'll show you examples of applying the rules, but I think it's useful to have the rules in one place. So here we go. Rule number 1. Treat ions separately. That is, ionic bonds themselves never have Lewis structures. If you have an ionic compound, you could conceivably have Lewis structures for the cation and separately for the anion, but not for the ionic compound. Once you've separated them, or if you have a molecule, count up all of the valence electrons in the structure for which you want to draw a Lewis structure. All of these electrons must be shown, and these are the only electrons that you can work with to apply each of the following rules. As you use up the electrons in forming bonds or showing non-bonding electrons, remove them from your running total of unused valence electrons so that you know that you've used up all of the electrons. Third, use some of those electrons to form bonds and assemble a bonding framework, which I'll call a skeleton structure, by using 2 electrons per bond. Now this is where a lot of the trickiness comes in, knowing the correct order in which to attach the atoms, and I'll try to give you clues for how to do that as we go. Sometimes you can tell the order of the atoms from the formula because often the order of atoms in the formula tells you the correct order. In polyatomic ions or polyatomic molecules, the central atom is often shown first. Not always. Water is an exception. H2O, the central atom is oxygen. But often it's shown first. And very commonly, the more electronegative atoms, like fluorine, tend to be outer atoms all connected to one central atom rather than being central themselves. Step 4. Once you've assembled the bonding framework, if you have any remaining electrons, start completing the octets of outer atoms. By an outer atom, I mean an atom to which there is only one bond. That's the definition of outer atom. And keep in mind that hydrogen always only has 2 electrons. So if you bonded a hydrogen, you're done. That's completed the octet. There should never, ever be dots shown on hydrogens. Step 5. If you still have electrons left over from the valence electrons that you counted up after you've done this, then those electrons must be assigned to inner atoms as pairs of electrons where possible, even if that exceeds an octet on the inner atom. Okay? Once you've done this, we have, after Rule 5, we have what we will call a provisional structure. Provisional Lewis structure. We have 2 more steps to apply to get a final Lewis structure. We may be done at this point, but we have 2 steps to check, and in order to do these next 2 steps, I have to define a new term. Formal charge. By formal charge, what we mean is the charge that an atom in a structure would have if all of the bonding electrons were shared equally. That is, ignoring electronegativity differences. What we mean is any electrons in a covalent bond are shared exactly equally between the 2 atoms. Now let's figure out how many electrons are around that atom and whether it has more electrons than it wants or less than it wants, so that whether we can determine whether it has a negative charge or a positive charge. This idea of formal charge, the formal part, is in the sense of a formality. It is not a true charge, but merely an accounting method that we're going to use to keep track of where the electrons are. In practice, calculating formal charge is relatively easy. We're going to calculate the number of valence electrons. This is from the periodic table. That is, we just look up the column containing that element. That tells us the number of valence electrons. And then the dots and dashes are from the particular structure that we're looking at. Okay, so let me look at some examples here. In the provisional Lewis structure shown here, if I count up the formal charges, hydrogen has a valence of 1. It has 0 dots, and it has 1 dash, so the formal charge is 0. Carbon, it's in column 4 on the periodic table, so when I look up the number of valence electrons, it's 4. It has 0 dots on it, and it has 2 dashes, this one and that one. So it has a formal charge of 2. Notice I've drawn the line across that bond there. The idea here is if this bond is shared equally between hydrogen and carbon, then half of the electrons count towards the carbon, half count towards the hydrogen. Therefore, we have 2 nearest electrons on the carbon. It wants 4 because it has a valence of 4. 4 minus 2 is 2. That's why this works. Lastly, let's do the nitrogen. Nitrogen is in group 5 on the periodic table. It has 1, 2, 3, 4, 5, 6 dots in this structure and 1 dash. 5 minus 6 minus 1 is minus 2. There's the formal charge on the nitrogen in this structure. Notice this is a formal charge in a given structure. Nitrogen may very well have different formal charges in different structures. One more example. In this ion over here, first of all, the square brackets and the charge here are meant to represent that the entire structure has collectively a -1 charge without specifying which exact atom the charge is on. That's all the square brackets are about. If we look at the oxygens, oxygen has a valence of 6. This has 6 dots on it and 1 dash. So this has a -1 formal charge. If we look at the bromine, bromine is in group 7. It has 2 dots and 3 dashes, so it has a formal charge of +2. Okay. Lastly, notice that if you add up all of the formal charges in a structure, it must equal the charge on the overall structure. In the first example that we looked at above, 0 plus 2 minus 2 equals 0. That's the charge on this overall species. Over here, you have to count the formal charge of -1 on each of the oxygens. So -1, -1, -1, that's a total of -3, plus 2 gives us a net charge overall of -1. If the sum of the formal charges doesn't add up to the charge on the structure, you've done something wrong and you need to find your mistake at this point. Either you've calculated formal charges wrong, or you've counted your electrons wrong, or both, but there's a mistake somewhere and you need to find it. Now that we have formal charge defined, let me add 2 more rules to forming Lewis structures. So rule number 6, calculate the formal charge on each atom in your structure, and then in order to get the best structure, you want to minimize the sum of the absolute values of the formal charges by forming multiple bonds as possible in your structure. That is, use some of the non-bonding electrons to form double or maybe even triple bonds so as to minimize the total amount of formal charge in the structure. I'll show you examples. Keep in mind, as we said in the last slide, the sum of the formal charges must equal the overall charge on the structure. And the best structures always avoid placing positive formal charges on very electronegative atoms. So for example, fluorine will never, ever, ever end up with a positive formal charge. All right, so in a subsequent video, I'll work through some examples of applying these rules in detail. So watch that video next.